Stripping down science. The Naked Scientists.
Hello and welcome to the Naked Scientist Show. Chris is away for the next couple of weeks, so you've only got me, I'm afraid, Dr. Kat, and the delightful Dr. Helen.
Hello.
So what are we going to be doing today? We've also got the very handsome Petro in the studio, who's doing all the really complicated stuff with knobs and faders to make it all work. On this week's show, we're going to be discussing the latest developments in cancer research. Could understanding stem cells be the key to beating cancer in the future? And how are new technologies helping us to find out more about the genes involved in driving the disease? To get to the bottom of it, we're joined here in the studio by two fantastically knowledgeable guests, Professor Fiona Watt from Cambridge University and Dr. Andrew Futrell from the Sanger Centre in Hinxton. They're going to be here to answer all your questions about the latest developments in cancer and research, and that's not all we've got lined up. Helen?
No, that's right, of course. Today we will also ask you if you'd like to take part in kitchen science and make your own electric slime. Doesn't that sound fantastic? What you'll need for that is some vegetable oil, some corn flour, a mug, a spoon and some polystyrene or a balloon. So gather those things together and stand by and we'll tell you what to do with them.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, later on the show, we're going to be discussing the role of stem cells in cancer, but there's been a really exciting stem cell story in the news today. I mean, I used to work on stem cells, so I've got a real soft spot for them.
Quite close to them, are you, Kat?
Maybe not these ones. Anyway, in 2006, Professor Karim Nayernia, I think that's how you pronounce it, I should have checked this first, he hit the headlines when he persuaded mouse embryonic stem cells to turn into sperm-producing cells, and then could use sperm from these cells to lead to the birth of healthy baby mice. That was incredibly exciting at the time. And now the professor and his team have managed a similar fate of biological engineering, but using stem cells taken from human bone marrow. Now, these stem cells aren't normal bone marrow stem cells, but they're called mesenchymal stem cells. They're a slightly different population. And they're one of the most malleable sorts of stem cells we think we know of in adults. And they've been found to grow into other sorts of body tissues, including things like muscle. They're really exciting cells. So what the research team have done is grown these cells in the laboratory and treated them so that they develop into male reproductive cells, known as germ cells. And they found some partly developed sperm cells called spermatogonial stem cells in amongst this. And that's one of the early steps on the road to sperm production. And so the next goal, of course, is to see if you can actually turn these into mature sperm. Maybe it will work. It's going to take a good few years. But these kind of results, these kind of experiments are really exciting because they're looking at adult stem cells. There's been a lot in the news about embryonic stem cells and their power to turn into many different sorts of things. But there's lots of ethical questions about using stem cells taken from embryos, and particularly from human embryos. So if we can find really malleable cells from adult stem cell populations, and we can talk to Fiona a bit about this later, then that could be a really exciting way to generate new cells in the future. Helen?
That sounds excellent. And is there a problem with the need to produce sperm in some men? Would it be a kind of treatment for them, men who can no longer produce their own sperm, perhaps? And this could be a route to kind of getting them back on track to having their own babies?
It could be, but
is that
we'll
kind of one of the
actually works?
I guess it actually works. Fantastic.
Ask that question when it works.
Okay, cool. Well, I've got some slightly gloomy news. Usually, as I do, bring you some nature stories, but this is from the world of conservation. And it seems that the opening up of forests by roads for logging companies is leading to the demise of forest elephants in West Africa. And that's according to a study recently published by a team of scientists from the World Conservation Society, usually known as the WCS. And they trekked for more than 8,000 kilometres through the African forest to conduct a census of elephant numbers. Now, counting forest elephants is not an easy business, partly because the dense forest means that unlike their cousins that live in the open African grassland savannas, they're called the savannah elephants. You can just fly over in an aeroplane or a helicopter and easily count them and get an idea of how many there are because you can see them. But in the forest, it's far too dense and you can't do that. And in any case, you actually don't want to get very close to these forest elephants because they're really quite well known for being aggressive and dangerous. At least you don't see them until they're up close and they might be scared of you as much as you are of them. So it's not a really good idea to get too close to them. So instead, what the research team did was that they hunted for clues that the elephants have left behind in the forest. And the most reliable way of knowing that an elephant's been there is their dung. Now, worryingly, the team found that the evidence for only very low density of elephants, less than perhaps 1 in every square kilometre of forest. This is from counting these kind of and finding piles of dung, essentially. And perhaps even more of a concern is that there are fewer piles of dung left near to the logging roads. These are the roads that are being built further and further, penetrating into these forest areas in West Africa, and in fact in many areas of forest around the world, to allow timber companies access to the valuable trees. Now, instead of finding evidence for live elephants nearer to the road, what the scientists found were there were more elephant carcasses with the tusks removed, which really strongly suggests that these are the roads that are bringing in not just the timber companies, but elephant poachers who are after ivory and also elephant meat. Now, since ivory is an issue that perhaps we don't think about so much at the moment because supposedly there isn't allowed to be any trade in it according to international regulations. But since 2004, the price of ivory has quadrupled, and currently it's about $850 US a kilo, which is an awful lot. And it sadly means that basically this continuing demand for ivory could end up wiping out these incredible creatures. By their sounds of it, there really aren't that many of them left, which is very sad indeed.
That's bad news for elephants. No, not good at all. Anyway, I don't know what you were like as a teenager. Were you a teenage tearaway, Helen?
No, I was very well behaved, actually, like all good scientists should be. No, I was horribly well behaved. My parents are listening to this, I think, so they probably have something else to say. But how about you?
I was fairly well behaved. I had my moments. Petro, I reckon he had a moment or two. Yeah,
no, he's shaking his head.
You can see in his eye. Anyway, but it's well known that teenage kids indulge in risky or dangerous behaviour like smoking, drinking, doing drugs. Not that we advocate those on The Naked Scientist
Absolutely not.
at all. But now some psychologists at Temple University in the USA have suggested that this kind of risk-taking behaviour is actually just due to the way the teenage brain's developing, which could explain why expensive educational programmes aren't really working to try and cut down on these behaviours. Now, the researchers have been looking at all the research that's been done on the teenage brain over the past decade or so, and they think they've come up with the reason why adolescents really go for risky behaviour. And it's due to 2 different networks developing in the brain at different speeds. So you have a network called the socio-emotional system, which processes social and emotional information. And this starts developing during puberty. And it causes teenagers to become more easily aroused, to experience really intense emotions, and to be more sensitive to peer pressure and social situations. But you also have a system called the cognitive control system, which is sort of the brake to that, which regulates behaviour and helps you make mature decisions. But this really only starts working later in puberty and continues towards your mid-20s. So you have these 2 conflicting systems, and the one that makes you a bit crazy is developing faster. So this could explain why teenagers are taking risks and why they're also more likely to do so under the influence of their peers. The researchers don't really suggest many ways to get around this.
I suppose if we understand why it's happening, we've got more of a chance of figuring out exactly what's causing it and, maybe we at least understanding why the attempts we're making to change behaviour may not be working. I suppose that's at least the first step, isn't it?
Well, they're calling for stronger laws, basically. So if you make it, raise the age of sale for cigarettes and alcohol and increase availability of mental health and contraceptive services, you'll just get them through it.
Yeah, until your sensible part of your brain kicks in.
Yeah.
Sounds good to me. Well, how could I let the news section go by one week when I'm here without talking about the oceans? Yes. Once again, I have a story from the sea. And this one is about humpback whales, which are record-breaking swimmers. The news comes out this week because they have been found to migrate the longest distance that's been ever recorded for a mammal. OK, the birds probably win, maybe some insects. They do fly a long way too. But for the swimming mammals, the humpback whales definitely get the gold medal.
More than David Walliams.
He only managed the English Channel. That's nothing. That's about 20 miles, isn't it?
I'm sure he could do the Atlantic.
Perhaps now we'll kind of take on the challenge. David, if you're listening, humpback whales, they're doing it better than you. But this is all according to studies from scientists in the United States who have tracked migrating whales over 5,100 miles, all the way from Costa Rica in Central America to their feeding grounds down in Antarctica. And that's a long way, I have to say. That's pretty good. That's quite a few English channels worth, I reckon. But and the way they did this, it's quite an easy way of figuring this out. They didn't actually use anything fancy like satellite trackers or anything like that. They basically used quite a traditional technique that's been used for a long time in whale studies and dolphin studies, which is just recognising individuals from the shape of their tails. They have these huge tail fins called flukes. And whales often get little things, barnacles growing on them, nicks and cuts and kind of marks and so on, which you can actually take photographs of and then recognise later on, because they tend to persist over time. And so they looked at whales around Central America, and then they also had photographs from Antarctica, and they managed to recognise the same individuals that were moving all this way. And it's really quite exciting, apart from the fact that they're going these huge long distances. It's also the fact that we have shown for the first time what we've suspected for a long time, which is that humpback whales do migrate into warmer waters during winter. And a slightly more techie part of this study was that they use satellite data of the temperature of the sea surface, which you can do quite easily, and showed that during times when the water around Central America, around the equator, when it was a bit cooler, the whales actually migrated further north to find warmer water still. So they clearly want to keep warm while they're in that winter time, and then they head back down to Antarctica where they feed. So that's rather nice. I think it's a lovely idea to think of whales migrating all that way, thousands and thousands of miles.
The Naked Scientists, supported by the Wellcome Trust.
That's right, you're listening to The Naked Scientist, and now it's time you've all been waiting for. I hope you've collected all of your kitchen bits and bobs together, because it's time for Kitchen Science. This week, Derek and Dave are with Mark and Lauren in Haverhill, where we're going to be mixing together random things from the kitchen so that we can make electric slime. I can't wait to find out. Hey, Derek.
Hello there, welcome to Castle Manor Business and Enterprise College in Haverhill in Suffolk, and we've come here to do a brilliant experiment which you can do at home, so please listen out for the details. With me, of course, is Dave, who's going to tell us very briefly what kind of stuff we're going to be doing.
We're going to be building electric slime.
We're going to be building or making electric slime. OK, fantastic. And also, we've got a couple of guys who've come down from the college here to help us out and do the experiment, so could you guys tell me your names and what years you're in, please?
Mark, Year 11.
Lauren, from Year 11.
OK, good stuff. And just quickly, I want to find out whether you guys like science and whether you might be into the experiment we're doing. So what kind of science do you like, Mark, if anything?
I like all sciences, but particularly biology, I'd say.
All right, OK. And yourself, Lauren?
Better at biology.
So does that mean you actually like biology, though?
Yeah.
Good stuff. Well, I'm glad. We're probably going to do some, I don't know, vaguely chemistry, physics-y type stuff, so maybe we can get you into those sciences too. OK, then, so if you want to do this at home, then here's what you need. You need some corn flour. You need some kind of mug or something, and try and make sure it's dry. OK, a spoon, OK, is good, and, you know, probably a tablespoon size type thing is fine. Some oil. Any particular kind of oil, Dave?
Just general vegetable oil.
Vegetable oil is fine. OK, and then basically a block of polystyrene is good. This is something that we're going to use to generate static, basically. So does anything else do apart from polystyrene?
Even a nylon jumper or a balloon, just something like that.
Yeah, blown up balloon, yeah. OK, fair enough. Good, OK, and then you've basically got to listen to what Dave is now going to instruct Mark and Lauren to do. So what do they do, Dave?
OK, Mark, if you'd like to put 3 or 4 teaspoons of corn flour into the mug.
OK, in it goes.
OK, now, Lauren, could you kind of put in enough vegetable oil in there to make quite a thick mixture and mix it in really well?
OK, so there we go. We've got kind of about the same amount of oil, maybe a bit less, compared to the amount of corn flour we had in there. And now we need Lauren to mix it up, basically, so go for it.
You want to get it into a really nice, smooth mixture. It should be reasonably thick, but still flow quite easily.
OK, so we want something that's treacle or maybe a bit kind of easier flowing than that.
Not as thick as treacle, somewhere around there, though.
How easily does that mix, Lauren?
It's mixing quite well.
Does it look like anything in particular to you?
Rotted butter.
Rotted butter. A lovely thought. OK, well, it certainly does look like something I would not choose to eat. But, yeah, maybe some kind of icing, or, you know, before you pour it on a cake or something, I don't know. But I'm sure not quite as tasty. OK, fine. How's that looking, Dave?
We want to get all the lumps out of that, give it a good stir. And then we're going to want you to rub whatever you're using to pick up the static, the polystyrene or whatever, on your hair, get it really nicely charged up, and then pour this slime off the spoon and move the charged up thing near it and see what happens. OK, so
that's what you've got to do. So basically you've got your gloopy mixture, which is corn flour and vegetable oil mixed together in kind of the right proportion, so it's kind of gloopy, maybe a little bit easier flowing than treacle, but not a lot. And then you basically take your static thing, which could be a piece of polystyrene rubbed against your hair, and then you wave that near to the kind of stream of corn flour oil stuff as you pour it off the spoon back into the mug or whatever you've done the mixing in, and see what happens, basically. So, yeah, move it quite close to that stream as it pours downwards. We're going to go back to the studio and not do that yet, but Mark and Lauren, I wonder what you think might happen when we kind of wave it close to that stream. Mark, any thoughts?
I'm not quite sure, but I think it's going to be messy.
OK, fair enough, yeah. Well, we hope so too, actually. We like messy science here, in a way. OK, and Lauren, what about you? Anything you think might happen?
Don't know.
All right, OK, so, well, that's fair enough. We'll be back here at Castle Manor Business and Enterprise College in Haverhill later on in the show, and until then, it's back to you in the studio.
Thanks, Derek. So in case you missed any of that, what you need to do is mix together some vegetable oil and corn flour until you get a lovely, thick, creamy consistency. Then you need to rub some polystyrene or an inflated balloon against your head until it's all charged up and your hair is standing on end. And then move the charged bit nearer to a stream of the slime. So you can make a stream of the slime by pouring it from one cup to another or by letting it drip off a spoon.
Well, we've had lots of questions in already. One of the questions we're going to discuss here is a question from Delano Mills, who's in Solihull in the West Midlands. And what he wants to know is, how does the body decide what genetic information is passed down to the following generation? And how do genes recognise things that start out being skills, such as musical ability, artistic ability, or even football skills? For example, he says, apart from me, no one among my brothers and sisters are musical, although my mother used to play the piano. He also says he thinks Naked Scientist is great, which is always nice. I thought we'd sort of throw this open. Now, the idea that characteristics that you acquire in life can be inherited is a bit sacrilegious to geneticists. It smacks of Lamarckism, the idea that, the characteristics you acquire in life could be passed on. But with things like skills, as far as I know, there's not a lot of evidence that they're particularly genetic. I don't know. Do any of our guests have anything to say?
There's
This is Andrew Futrell, by the way.
There is genetic data actually that says things like the ability to recognize perfect pitch, for instance, can be. There is a genetic component to it. It's not completely inherited, but there is a group of individuals who seem to have a genetic propensity to be able to recognize perfect pitch, and if you say that translates into the ability to sort of reproduce music more accurately, then one could argue there is some genetic component to at least the propensity to be able to do it should you decide to, given all the other influences maybe going on around you.
So it's a combination of nature and nurture.
That's probably the safest guess.
OK, I hope that answers the question. Helen?
Well, I'd say, actually, just going to chip in here, I'm not a geneticist, but I'd say surely all these skills we learn, they're based on so many different aspects of your muscle ability and all, it's not one thing that's going to be determined so sort of strictly by a gene, but there's got to be some influence in there, I'd say. And, and yes, it's also how you're nurtured and so on, like as you said. But, I think sometimes there must be some things we can pinpoint that would be passed down, I wouldn't know. Again, Mum, Dad listening, what do you think? Which of those traits would pass down to me? I don't know. But I think it's a good question. It's a great question.
Yeah, it's interesting. If any of our listeners have got stories of music running in family, I come from a musical family myself, or any other particularly interesting skills that run in your family, then do let us know.
Yes, Kat, we can't get her off the musical things. Pretty much what she spends the rest of our time doing. Now, remember, we do love to hear from you. Thanks so much for everyone who keeps in touch with us over the website and so on. I've got an email here from Ken Nguyen. Oh, I knew I said this wrong. Nguyen, I think it is. Sorry, Ken, if I got that wrong. From the UK. And he says, "Hi, Naked Scientists. I just wanted to let you know that we have the best science radio show on earth," which is just wonderful. Thank you. He says he loves the way we set up the show and the website, which has just been renovated. So if you haven't been to see it recently, have another look at the website. That's www.thenakedscientist.com, because we have launched a whole new platform there. Loads of things to look at. Keep you entertained for hours. But Ken, thanks ever so much for your email. He says, keep up the wonderful job, and we will, definitely.
Well, on today's show, we're talking about the latest progress in cancer research, and we'll be talking later to our guests, to Fiona Watt and to Andrew Futrell. But when it comes to cancer, prevention's always better than cure, and there are several ways that people can reduce the risk of cancer. For example, I've been out and about over the past few days in the sunshine, spreading the message on behalf of Cancer Research UK's SunSmart campaign, warning people about the risks of sunburn. Sunburn can actually double your risk of skin cancer, so it's really important to be safe in the sun. But are sunbeds a safer alternative? Let's find out now in Bob and Chelsea's Science Update.
This week for The Naked Scientists, we're going to highlight 2 ways you can lower your risk of cancer. I'm going to answer a listener's question about suntanning, but first, Chelsea has this report on new research that could help smokers quit.
Most smokers will tell you that a cigarette tastes especially good with a beer or a cup of coffee. But a new survey has revealed that to some smokers, cigarettes taste especially bad with milk, fruits, vegetables, and water. Clinical psychologist Joe McClernand of Duke University says that was surprising, and the finding could lead to a quit-smoking diet.
It would make a lot of sense to me to develop a diet that could be used to help a smoker not gain weight once they quit smoking, but also maybe be used to help the smoker enjoy smoking less before they even quit smoking so that it's easier after they do.
McClernand adds that menthol cigarettes seem to clash less often with foods, possibly explaining why some people prefer them over other varieties.
Thanks, Chelsea. Everyone knows, or we hope everyone knows, that baking in the sun's ultraviolet rays damages your skin and may lead to premature aging and cancer. But with bathing suit season on its way, Jessica Vega of Gainesville, Florida, emailed us to ask whether tanning beds are a better solution. We turn to dermatologist Stephen Stone of the Southern Illinois University School of Medicine.
No, tanning with a tanning bed is definitely not better than sitting out in the sun. The degree of tan that you get is a sign of damage to your skin, and whether it's natural ultraviolet or artificial ultraviolet, a given tan is a given sign of injury.
He and other dermatologists are hoping to change the cultural preference for tan skin. But for those who insist on a tan, he recommends using sunless tanning lotions inside and a strong sunscreen outside.
Thanks, Bob. We'll be back next time with stories about hurricanes, droughts, and other extreme weather. Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Oh, thanks, guys. And if you want to hear more from Bob and Chelsea, then you can go and check out their Science Update website, which is www.scienceupdate.com.
Fancy listening to the Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
Hello, that's right. You're listening to The Naked Scientists, and Kat and Mia are in charge this week. Chris is away. Hooray! But so I hope you're enjoying the show without Chris, but he will be back soon. Anyway, over the past few years, some researchers have found evidence to suggest that stem cells may play an important role in cancer. Now, Kat's already been talking to us a little bit about stem cells already today, but we sent out our roving reporter, Sabina McKinowitz, to find out more.
To begin my quest in exploring the role of stem cells in cancer, I thought I'd find out what a stem cell is. So I went to the Wellcome Trust Centre for Stem Cell Research and I asked a stem cell researcher.
Stem cells are a really amazing cell type. They are defined by two very special properties. The first is self-renewal. Self-renewal is the capacity to make identical copies of themselves. And the second property that defines a stem cell is the ability to differentiate into more specialized cell types. We break stem cells into two different categories, if you like. Embryonic, which have the capacity to make any type of tissue, and then more specialized stem cells, which we call adult stem cells, which are restricted to a particular type of cell, be it brain tissue, be it skin tissue, and so on.
Jason Ray, who's researching stem cell programming. I'm off to see John Stingle, breast cancer specialist in Cambridge University's pathology department, to ask him what cancer is and how stem cells are involved.
We actually believe that cancer is a disease of stem cells. Stem cells are normally involved in the formation of an organ, and all cancer is organ formation gone wrong. Cancer is a disease where you require multiple genetic mutations to get a tumor. For example, if you don't have just one mutation and get a tumor, because if that was the case, we would all be dead. So you actually probably need 5 to 7 mutations. The probability of a cell getting a mutation is actually very low. It's like 1 in a million. It's kind of like trying to win a lottery prize. However, if you have a cell that has the capacity to produce lots of daughter cells, such as a stem cell, if you can mutate a stem cell, but then that stem cell produces 1 million daughter cells, now you have 1 million cells that already have one genetic mutation. So your probability of one of those cells getting a second mutation is actually quite high. And then one of those cells, that cell that becomes mutated, it'll produce 1 million daughter cells. And one of those will become mutated, and so on. And that's how you can acquire, say, 5 mutations.
A lot of research is being conducted to look at how stem cells work and what their role in cancer is. Brian Huntley is an expert in stem cell self-renewal, and he's working with leukemia at the Cambridge Institute for Medical Research. I asked him how current research is directed by a need for better cancer treatment.
Treatment of malignant disease is still very ineffective, and most patients have relapse and progression of disease, and many patients still die from the malignant disorders. However, when you initially have a tumour, and regardless of the tumour type, and regardless of the therapy, whether that be chemotherapy, whether that be radiotherapy, or some of the neuroimmunotherapies, there is usually a reduction in the size of the tumour mass. Sometimes it's very dramatic, sometimes it actually disappears. However, we know that the vast majority of patients have regrowth of that tumour, either in the same place or what's called a metastasis, so that's in another place. And that would suggest, following on from the cancer stem cell hypothesis, that we are killing the cells that form the bulk of the tumour but are not able to regrow it, whilst we are sparing the cancer stem cells. We would ideally want to target the critical cells which cause the propagation and the regrowth of the tumour. We need to know more about these cancer stem cells, how they differ from normal stem cells, and we need to be specifically targeting them to show improvements in cancer therapy.
That was Sabina Mikinovitz getting to grips with cancer stem cells.
So now in the studio we have Professor Fiona Watt from the University of Cambridge, a woman who I've known for some time. How are you doing, Fiona?
I'm doing fine, thanks. Nice to see you again.
So your research is looking basically at cancer stem cells and stem cell biology. We'll go right back to basics here. How would you define cancer? What would you say it is?
I'd say it's a disease in which cells in a part of your body start to grow in an uncontrolled way. Sometimes that will result in formation of a lump, for example, if it's in your breast. But if you've got cancer in your blood, the cancer cells will be flowing around your body. And then, of course, the dangerous thing is if the cells start to spread to other parts of the body.
So we've just heard from Sabina and the researchers she's been speaking to about the idea of cancer stem cells, which is quite new. How long has this idea really been around?
Well, you're actually wrong when you say it's quite new.
It's new to me.
It's an idea which has been knocking around for, some would say, almost 100 years since people first started looking at cells in cancers. And even back then, looking under the microscope, people could see that not all of the cells in a tumour were the same. And so the idea is that some of the cells in the tumour are essentially innocuous, and other ones, the stem cells, power the growth of the tumour and ensure that no matter what you do to try to get rid of the cancer will eventually regrow.
And what sort of cancers so far have we found stem cells in? Because there seems to be new reports coming out all the time about it.
Yes, I think the first and most compelling identification of a stem cell in a tumour was work which was done on leukemia, so cancer of the blood. But there have been very exciting reports of identifying stem cells in breast cancer, colon cancer, and other types of tumours. For example, something called a squamous cell carcinoma, which could affect your mouth, your esophagus. And so it seems really that almost every week evidence comes out for a stem cell population in another type of cancer.
And as we heard, these discoveries have quite important implications for how we're treating cancer. I mean, what can we do with this knowledge now to take it forward?
Well, you're right that it's very important. What we need to do is now design treatments which will target the stem cells rather than the bulk of the tumour. For example, many current treatments for cancer are based on the idea that these are the cells which are growing very fast. However, it might be that the stem cells are actually quite sluggish, and so you're not doing any good just getting rid of the fast-growing cells. So our idea is that we might be able to develop treatments which are more specific and are probably gentler for the rest of your body. They're not going to wipe out all of the normal cells which happen to be growing fast. So that's the hope, and that's why people are really excited about stem cells now.
So tell us a bit more about what's actually going on in your lab. I mean, you work on skin and the cells in there. What's new there?
Yes, well, my lab works on skin cancers, and there are two main areas that we're interested in. One is trying to find out how different kinds of cells in the skin contribute to cancer. So we want to identify the stem cells that drive the cancer, but we're also very interested in sort of essentially bystander cells that seem innocuous. They might not be dividing themselves, but we've found out that they can actually be communicating with the stem cells and giving them encouragement to grow, or else potentially holding them in check. So this whole issue of what are different kinds of cells doing in a tumour is very interesting to us. And then the other thing that we're working on is why is it you get different kinds of tumour? So in the skin, you've got the outer covering of the skin, you've got sweat glands and hair follicles and so on. And in different kinds of skin tumours, they're sort of caricatures of those normal sorts of differentiation that are going on. And we'd like to understand how that works too.
So tell us a little bit about there's two real divisions of skin cancer. There's non-melanoma and melanoma. What's the real difference between those two?
Well, the difference is that the two types of cancer affect different cell types. So melanoma is a disease of the pigment cells of the skin called melanocytes, whereas non-melanoma affects the cells that my lab works on, which are called keratinocytes or keratinocytes, depending on
where you come from. And what you fancy. So how is the discoveries that you're making, how are they going to feed into treatments for cancer in the future?
Well, we have very good links with a lot of the clinical departments at Addenbrooke's Hospital. And so what we do is we look at real tumours from real people, come up with ways of trying to identify the stem cells, and then test the ideas that these are going to fire tumour development. And then we want to go back to our clinical colleagues and say, well, look, can you think of new treatments based around what we now know about the stem cells in the tumours?
So it's being a bit smarter about drug development, finding the targets and then finding the treatments.
But as you know, it's a slow process, and you're really looking at probably 10 years from getting a good proof of principle to having something which would benefit a patient in the clinic.
Thanks. And finally, I can't let you get away without asking you to comment on the news story that we did earlier, the one about creating sperm precursor cells from mesenchymal bone marrow cells. What do you think about that?
If I were a man and I wanted to have a baby, I would not choose that route.
Really?
I wouldn't be very optimistic.
They're fascinating cells, though, the mesenchymal stem cells. They're really
mesenchymal stem cells are great. You can make bone, you can make more fat if, for example, you felt you were underweight.
If we were.
You can do lots of good things, but I personally wouldn't use them to try to make sperm.
You say mesenchymal. Can we say mesenchymal? Is that one we can have a different pronunciation of?
You can do that if you want.
Again, depending on where you're from. We're also joined in the studio by Dr. Andrew Futrell, who's from the Sanger Centre out in Hinxton, a little way south of Cambridge. I bet it was a lovely place to be today in the sunshine. But
yes.
Were you at work today?
I was not at work today, unfortunately, or fortunately, as the case may be.
Well, fortunately for you. Well, Andrew's been involved in what I think is a really fascinating paper, in the sort of area that I work in, which is for Cancer Research UK, which has been an enormous task, looking at hundreds and hundreds of genes involved in cancer and trying to increase our understanding of how they drive the development of the disease. So, Andrew, can you explain in a bit more depth what you've actually done here?
Yes. What we set out to do was to try to understand what role a specific set of genes that occur in the genomes of all individuals, and these genes are called kinases. We wanted to understand which of those genes were undergoing mutation. If so, which of those genes might be give evidence that they might be contributing to the formation and the ongoing sort of progression of the disease. And these genes are quite interesting because they essentially govern most every molecular process that goes on inside a cell. They're like molecular switches. They turn things on and off. And so we know cancers are characterized by sort of three main, my version of cancer is they grow when they shouldn't, where they shouldn't, and how they shouldn't. Pretty much all of those processes have a kinase involved somewhere in the pathway that governs those processes. So we were interested to know which of those genes might be sort of interesting to think about in terms of drug targets. We knew also from probably the last 20 years' worth of research looking at cancer genetics that if you look at the genes that are already known to be mutated and contributing, protein kinases show up more frequently than any other gene family at the moment.
So they're the real sort of bad guys.
At the moment, they appear to be the bad guys we understand the most about, and probably the linchpin for deciding to work on those genes to start with out of all the 20-some-odd thousand that exist in the genome was that is probably the one gene family at the moment we actually know how to make drugs to. There's several quite startling examples, at least from a cancer genetic standpoint, of understanding the genetics of a tumor via a mutated protein kinase and developing a small molecule that actually does have quite high levels of efficacy in patients. So that's sort of the context. So we We wanted to understand the genetics of cancer, but also start in a family where if we found something, hopefully there would be a shorter route to translation in terms of patient benefit.
So I understand that you looked at more than 500 genes in 200 types of cancer. That sounds absolutely colossal. How do you go about looking at that many genes for that much information?
We used a fairly, what is probably in the next couple of years going to be sort of Stone Age technology, actually. We use the same type of technology that we use to sequence the human genome, and that's using this sort of what's called capillary-based gene sequencing, not some of the newer single-molecule fancy techniques that everybody's going on about these days, which we hope to use as well. But this was pretty much brute force stuff. So out of those 500 genes, we looked at all the bits that encode them, amplified them up using the polymerase chain reaction from all 200 samples across these 500 genes, which works out to be about 10,000 fragments per sample, and just sequenced them from both ends.
That's a lot of work. How do you cope with that much information? And you've presumably got to have incredible computers to process that information and find what's in it.
It became relatively apparent to me early on when we started this project about 7 years ago that my general mode of organization, which is sticky notes, probably wasn't going to cope. So we now have an excellent group in the Cancer Genome Project of about 14 people who go under the collective heading of bioinformaticians, and they're really a brilliant group of people. They organize the data, they give it to us in terms we can understand, and they actually allow us to find a single experiment amongst the sort of millions that have been done, which is actually quite important. So it is a huge collaboration between lab scientists, computer scientists, and the people to sort of integrate the information between the two.
So what did you find? What were you expecting to find, and what did you actually find?
Well, what we hoped to find, we'd done work early on in sort of pilot studies that found a frequently mutated protein kinase called BRAF in the tumor type we were just talking about, melanoma. And this particular kinase is mutated in about 60 to 70% of this particularly lethal disease if it progresses. And what we were hoping was that was sort of the pattern that one was going to find when you started looking at kinases across a broader set of cancers. For the very reason that 60% of a gene being mutated in a tumor makes it a good drug target if you can build a molecule to turn that gene off. So we started doing this study on the 200 cancers and relatively quickly began to understand that particular example unfortunately looks like the exception rather than the rule. The rule looks like a much more widely distributed set of mutations across a larger number of genes. So we looked at found about 1,000 mutations in 200 samples, of which we believe, using various sorts of approaches, including statistical assessment, about 100 of those are probably driving cancers in that group of 200.
So this is more than you expected?
I think it's quite a bit more than I would have expected, and certainly more than we hoped. We hoped it would be lots of spikes rather than this rumble of noise, because it's much more tractable to deal with the spikes in terms of therapeutic development.
But even so, do you think that means you've potentially got more targets to have a go at?
I think that's exactly right. I think what it does, it opens up a window into understanding just how complex the disease is, and that's sort of a rather daunting sort of perspective. But I think what it also does is allow you to begin to integrate this information into understanding what processes, what pathways, what signaling sort of circuitry is actually turned on or turned off in particular cancers, and maybe give you an opportunity to not actually go after the gene itself, but also the pathway. I think cancer is a complex disease. We can't get away from that. So I think we're going to have to get in there, roll our sleeves up, and really get to grips with it, sort of the ugly reality of it now.
So you've looked at kinases, these particular group of signalling molecules. Are there any other groups that you think are next on your hit list, families of molecules? We've started a study sort of running concurrently towards the end of the kinase study, looking at another group of about 4,000 genes this time, and we're going to use larger numbers of tumors, about 100 cancers per set. And this is comprised of essentially any gene family where there's already been one member of that family to be shown to be mutated in cancer, promoting this idea that they may cluster by family or by function, including things like DNA repair. We know DNA repair is not working particularly well in a lot of cancers, things like the phosphatases, for instance, which turn things back off after kinases turn them on. Other gene families that are involved in sort of signaling pro-growth, pro-apoptosis, cell growth, division, all the usual suspects, at least as good as we can come up with that list at the time. So that's going to keep you busy for a bit. Yeah, I don't think we'll unfortunately work ourselves out of a job anytime soon.
Sorting out the sparks from the quarks, the Naked Scientists.
You're listening to The Naked Scientists with Kat and Helen. Chris is on holiday, and we're talking about the science of cancer. And we've got a few questions in the pipelines we'd like to answer on that topic. But first of all, I shall jump in with a question that came in just now from Alan in Orpington about my whales. Thanks for getting in touch, Alan. And he says, whales are mammals, but they only consume salt water. Is this dangerous? This is dangerous for land mammals, so do sea mammals filter out the salt? Well, actually, Alan, not all whales and dolphins and other mammals, like seals and walruses and so on, that live in the sea, they don't all actually drink seawater. So that begs the question, where do they get their water from? Because that's obviously something that mammals need. And in fact, we think what happens actually is a lot of these mammals gain their pure water, if you like, the pure non-salty water from the food that they eat. And they are able to extract that from the fish and so on that they consume. But there also are other adaptations they have in their kidneys, because that's the key, really. The reason we can't sit down and drink seawater is that our kidneys just can't deal with it. We're not used to that. It just cannot. Our kidneys can't cope with that much salt. But the whales and dolphins have got special kidneys that can deal with large quantities of salt concentrations. So they can actually manage to do that. So it's partly that they don't actually necessarily gurgle down all the stuff they're swimming in, and they get it from their food, but also that their kidneys can deal with it. But thanks ever so much for your question. I think now we'll get back to the topic in hand, which is the science behind cancer.
It is always nice to know that someone cares about whales, not just Helen.
Oh, come on. You all love whales.
Oh, they're pretty cute, as you know, apart from the baleen ones with the big flappy face. I don't like them. Anyway, we've got a question about skin cancer, which I thought I'd ask to Fiona. And it's a question in from Jan. And he or she says, why does skin cancer seem so much more prevalent now? Is it a new disease, or is it because people didn't talk about cancer in the old days? What's your take on this?
It's a good question. The non-melanoma skin cancers are by far the most common cancers in the Western world. And it's largely because your skin is the sort of barrier which is protecting you from the environment. So exposure, as you've heard, to sunlight, if it's uncontrolled, that's going to damage the DNA in your skin and give you cancer. Other kinds of damage which can result in cancer would be exposure to harmful chemicals. And so it's really, we think of the skin as really the front line in protecting our insides from the environment, and that's why it's so commonly affected by cancer.
Because actually, in over the past few decades, rates of melanoma, the most dangerous form of skin cancer, have, I think, nearly trebled, and particularly among younger people, and that's because people are taking holidays in the sun, using sunbeds. Is that the same for non-melanoma? Because that's also caused by sunlight, isn't it?
Well, it's true that the incidence of melanoma has really rocketed since the advent of package holidays in the 1960s. Somebody sitting very pale in an office for 50 weeks of the year and then frying themselves for 2 weeks on the Costa del Sol is really not good news for melanoma.
Hello to our listeners in the Costa del Sol.
But melanoma, people believe that's for melanoma, is the sort of exposure to intense sunlight. For non-melanoma, it's more long-term chronic exposure. So, for example, people who work, farmers, are at risk of developing non-melanoma skin cancer on the backs of their hands or on their faces. And so that's really sort of low-level but very long-term damage that triggers that sort of cancer.
So that's the answer for you. We have an email in from anonymous person who says, hello, Naked Scientist. I'm a 30-year-old man. I eat a healthy, balanced diet, which includes food high in antioxidants, but I'm hooked on sunbeds. Am I at risk? And I would certainly say, in my capacity working for Cancer Research UK, that yes, you are. Because not necessarily what you eat in your diet is going to be able to protect your skin in that way. And exposing yourself that regularly on sunbeds, you're still exposing yourself to ultraviolet radiation and increasing your risk. So it's a call you've got to take, but you're still increasing your risk. We've also had a question in from a man on a tractor. Not too sure, he doesn't give his name, who's asking us why aren't UK survival rates for cancer as high as those in the USA? Have either of our guests got any comment on them before I try and...
Well, I'm a PhD, not a medical doctor, but I do know medical doctors who would jump up and down and disagree violently with this assertion. But in terms of survival, it's all about avoiding getting cancer to start with, early detection, and then the best treatments. So I think if we could be more quick off the mark in getting to the doctor and getting diagnosed, that would improve our survival rates in the UK a lot.
And it's important to point out that UK survival rates are really improving for cancer. I think in the past decade, the death rate from cancer has dropped by about 12%. So it's not all bad, and things are improving. The other thing is that if you've been affected by cancer, either personally or someone you know, and you actually want more information about the disease, then you can talk to Cancer Research UK's nurse helpline, which is 0207 061 8355. And you can also look at the patient information website that the charity has, which is www.cancerhelp.org.uk. You are listening to The Naked Scientists with me, Dr. Kat, and Dr. Helen, and our guests who are talking about the latest in cancer research.
Laying the facts bare, The Naked Scientists.
Right now, it's definitely time for us to find out what was this electric slime business all about in our kitchen science. So we're heading back to Haverhill to see what happened. Hi again, Derek.
Hello there. Welcome back to Castle Manor Business and Enterprise College in Haverhill, where we're still here with Mark, Lauren, and of course Dave, who has set up the experiment, where we are going to be doing some stuff with some slime that we made earlier with some corn flour and some vegetable oil. Now then, Dave, I wonder if you could instruct these guys as to what to do next.
We've got this beautiful slime. Now, Lauren, I want you to charge up this piece of polystyrene on your hair as well as you can. Get it all nice and charged up.
OK, and we have actually been practicing this in the meantime. So there you go. Lauren's actually rubbing it on her head. How does it feel?
Nice.
OK, we kind of... nice. Fair enough. You can do it in your spare time if you want. But, I mean, we kind of earmarked Lauren as having appropriate hair. So there you go.
Mike, if you'd like to pick up a spoonful of the slime, probably with holding the cup under it. Now, start pouring it, and then if Lauren can move the charged up thing really close to it.
Straight on here. It just seems to shoot to the polystyrene. It seems to, I don't know, be attracted to it in some way.
OK, what can you see from there, Lauren?
Yeah, it doesn't fall straight down, it falls more to the side.
Is it falling as fast as it used to?
No, well, it gets faster as it goes towards the polystyrene, but as it goes down, it seems to go slower.
If I've got the polystyrene near it, it slows down. If I take the polystyrene away, it starts to flow again.
Ah, OK, so we're actually seeing something where we actually kind of freeze it on the spoon, don't we, when the polystyrene is near there, but as soon as we move it away, it actually just starts glooping again. Well, some crazy stuff going on there with the slime. OK, I mean, blimey. What do you think? Because we know that thing was electric, was charged, because we were kind of getting static out of it. So what do you guys think was happening there? Any ideas, Mark?
I don't know, the electrons maybe were, being attracted to the slime in some way, and it was just pulling it towards it.
OK, well, Dave, of course, has the answer. So what's happening here, Dave?
Well, first of all, if you rub a piece of polystyrene on your hair, it tends to drag electrons out of your hair and stick them to polystyrene, because it'd rather be on the polystyrene than your hair. And this means that the polystyrene gets a negative charge. Now, corn flour is lots of minute particles, little tiny lumps. They're about 0.010 of a millimetre across each of them. And they're suspended in this oil. Now, both oil and corn flour are quite good insulators, so you wouldn't have thought it would have much effect, being near a charged thing. However, if you put a little lump of corn flour near something that's charged, you'll find that near a negatively charged thing, the electrons will get pushed away, so that they'll move on to the far side. So the side nearest it will become positive, and the side furthest away will become negative. This will mean it'll get slightly attracted to it, so the whole lot will get pulled towards it.
So you kind of charge them all individually or something?
It's called polarise. You move all the electrons across them a little bit. And so you end up with these little things. They behave a bit like magnets, because one end's positive, one end's negative. And if you imagine having lots of magnets in a sea of oil, they're all going to try and line up in big, long lines. So instead of dealing with individual particles, which can move past each other really easily, you've got these big lines, which are much more slowly to move, so it becomes much more viscous and harder to flow. OK, so you're actually dragging these little polarised pieces of corn flour towards the charged piece of polystyrene. So is this like anything else people might have seen? Well, if you ever play with iron filings on a magnet, when instead of being electrically charged, the magnet's magnetically, you could say it's magnetically charged. And so when an iron filing goes near it, one end of it gets North Pole and the other end gets South Pole. And so if you imagine all these iron filings, one end being North Pole, one end being South Pole, it will line up head to tail, as it were, and produce those spiky things you may have seen when you played with iron filings.
Yes, exactly. So when you have a magnet near some iron filings, they just suddenly snap into a particular shape, don't they? It's all rather amazing.
They sort of look like a hedgehog.
Look like a hedgehog. There you go. All right, well, give it a go if you like. And I hope you've tried this experiment at home. And if not, then please do give it a go. We've had a lot of fun here. Mark and Lauren, have you enjoyed the experiment? Lauren?
Yeah.
OK, fair enough. And are you delighted that because you were worried that we were going to put the gloop in your hair, but we didn't do that. So are you happy?
No, my hair's gone a bit crazy, though.
Oh, right, OK, after your, getting static out of your hair. All right, well, I hope you can go and sort that out. Excellent. And Mark, you enjoy it?
Yeah, it was nice and messy, and I was a bit disappointed that we didn't get it on Lauren's hair, but still really good.
All right, well, there's more time for that off air. Good. OK. Well, that's all from here anyway in Haverhill. So from Dave, myself and Mark and Lauren, it's goodbye back to the studio.
Thanks, guys, for your messy fun. It all sounds like great fun. I'm going to have a go at this after the show myself, I think. And on next week's Kitchen Science, Derek and Dave will be back with an overgrown bicycle pump. But they warn me that it's going to involve fire, so possibly not one to do at home, but definitely tune in next week to find out what it's all about.
We also had an email in earlier this week from Pad Chivukula, who's in the USA, who was asking us about cancer stem cells. Do you think we need a new class of pharmaceuticals to target cancer stem cells? So I really hope that we've actually answered your question in this show. We'd like to know what you think and what you thought of what Fiona and Andrew had to say about it.
I think that's about all we've got time for this week. But next week, I'm in charge, pretty much. Well, of course, I'm going to take you down into the oceans. How could I resist? Chris is away. So, fish it is. We will be talking about the science of the ocean. A very good friend of mine, Annalise Hagen, will be joining us to describe how she uses spotter planes with a special camera slung underneath them to pinpoint coral reefs that are in trouble. We'll be talking all about that and hearing about her exciting, exotic diving expeditions as well. Not at all jealous, possibly a little bit. But we'll also be joined by Stan Harpole from the University of California in Irvine. And he's found that adding fertilisers and chemicals to fields on land, is actually destroying biodiversity in the ocean. So we'll find out more about that odd connection there. So if you've got any questions at all about marine conservation, coral protection, anything like that, send them in to us this week and we'll have a go at it. So send us emails on chris@thenakedscientist.com and we will do our very best to include them in next week's programme.
And if you've missed any of the Naked Scientist programme today, you can catch up with a podcast, which you can find on our newly revamped website. That's www.nakedscientist.com. There's all sorts of stuff on there, articles about science, articles about things we've discussed in the programmes. We've got the forum on there too, so go on, log on and have a look around and interact with us. It'd be lovely to hear from you. That's about all we've got time for. We've got huge thanks to our guests, Fiona Watt and Andrew Futrell this week. Big thanks to the production team over in the Fishbowl. That's Ben and Sabina. And also to Fiona's little son, Angus, in there. And also for Petro for working the desk today. If you want to get even more science in your life, then you can check out the Nature podcast, which is available at www.nature.com/nature/podcast. And again, check out the Naked Scientist podcast too at www.nakedscientist.com. That's all for now. We'll see you again next week.